All right, before we dig back into talking about Lewis structures, are there questions? Okay, let me pop up my share screen thing. And we're going to talk about Lewis structures. All right, so the end of the previous session, we kind of got a little bit into talking about some of the rules, which are guidelines for helping you to draw Lewis structures. And we will call them rules, but one of them is more a rule and the other one is a little bit more of a guideline. So the duet rule is pretty much unbreakable. Yes, it does apply to two different elements, but one, because helium does not bond to other elements, it's too small. It already has both slots in its 1s layer filled. Yeah, we include helium in the duet rule because that's why it's called the duet rule, but it doesn't really apply quite the same way. Hydrogen pretty much has to obey this rule. There are really no ways to make it not obey the duet rule and still have a stable atom, well, stable molecule. The octet rule, that's the one that definitely sort of qualifies a little bit more along the lines of a guideline. So this is also why it says almost everything would like to have 8 electrons. We talked a little bit about where these things are on the periodic table compared to things we already know about them. In the previous chapter, we spent a little time talking about valence electrons. And note, we're kind of ignoring the transition elements. We're not going to pay an awful lot of attention to them for drawing of the Lewis structures. We had 1 through 8. Note again, we are ignoring helium. Helium is obviously above neon on the periodic table, but we're turning a blind eye to this for the purposes of the octet rule. So you have from 1 through 8. This also gives you ideas about what the desired number of bonds is. Desired is sometimes broken, but this is usually what you're shooting for. So the first column, the alkali metals, they like to have 1 bond. They only have 1 valence electron, so it's easier to share or give away the one they've got than to go steal 7 more from somebody else. The beryllium column, which is the alkaline earth metals, same sort of situation. You've got 2 valence electrons in that column, and it is easier to give away the 2 you've got than to get 6 more. By the time we hit the boron column, boron, aluminum, and sometimes gallium, you're heading toward the kind of make or break point. Most of the time, it's easier to give away or share the 3 electrons that the boron column has. But once you hit carbon, that really is truly the make or break. You either give away the 4 you've got, or you steal 4 from somebody else, or more likely you share 4 with some other atoms. And then you head back down. Nitrogen, phosphorus, sometimes arsenic, like to make 3 bonds most of the time. Oxygen generally makes only 2. Halogens most of the time make only 1. There are a few exceptions, especially further down that column. Things like iodine and beryllium. And then there's the noble gases, which for the most part hate everybody. They do not like to make bonds with other atoms. You can force some of the larger noble gases like krypton and xenon. However, things closer to the top of the table don't really have enough layers to their electronic structure in order for them to kind of fake their way through the system. All right, so all of that was sort of the end of what we were talking about pre-Thanksgiving. So now we are heading in the direction of being able to draw Lewis structures. You will sometimes see these referred to as electron dot structures or electron dot symbols. There are even some textbooks, however, that might gripe a little bit that there's a really subtle difference between the electron dot structures and the Lewis structures. We're going to treat them as if they were the same thing. So here are some words or some terms that we need to kind of deal with. One of them is called the unshared pair. More often, though, you may see it referred to as a lone pair. Two electrons, that's why it says a pair, that are not in a bond. They orbit a particular atom, but they aren't bonded to a second atom. You'll actually, I realized I have a bizarre word in here that I forgot what I was supposed to put the word in there. It says indicates King number. That's not what it's supposed to say. Indicates something. I don't even remember what I went to type there. Let's say indicates number of atoms. That's more correct. And the arrangement and the bonds. Structural formulas tend to be really heavily based on the visual end of things. We've got shared pairs, so bonded pair. One pair, meaning two electrons, and they are involved in a bond. We looked at this a little bit at the beginning of the chapter when we were talking about ionic and covalent and polar. So this kind of harks back to that. You will, and again, I've got some horrible typers in here. I've left out some of the letters in the word produce there. Blah. Yeah, at the end of the semester, and my proofreading skills have just sucked. Two bonds in the same area. You will often see these looking a bit like an equal sign between two atoms because it's two straight lines. And then we have a triple bond, three bonds in the same area, which is 6 electrons. There is no such thing as a quadruple bond or a tetrabond. You cannot put 8 electrons between the nuclei of 2 atoms. There is literally not enough 3-dimensional space to make this work. So singles, doubles, and triples, no quadruples. All right, so let's talk about the guidelines. So when you're drawing Lewis structures, one of the things you need to do is figure out how many valence electrons are you dealing with. Now, it does have to be the valence ones and not the total number of electrons for an atom, because we only want to deal with the outside layer. You are going to use one line per bond. One line indicates 2 electrons. I'm going to do something weird here, and I'm going to see if I can get the whiteboard to cooperate for me. All right, so I'm going to do draw. I'm going to do this. So I'm going to kind of go back and talk about this more later, but let me kind of show you what this looks like. So if that's a carbon atom, and I have a hydrogen bonded to it, This is a way of kind of showing you that there is a bond between the carbon and the hydrogen that's sitting there above it. Something else that you can do if you want to when you're kind of designing this, and this is a high school tip. This is what my high school chemistry teacher did, because when you're 16 and you're trying to do all the visual things, is he would do this. He would take his chalk and he would draw these little blobs on the end of the line, as this was sort of an introductory way to teach it to us, of a way to remind you that that bond that's occurring between the carbon and the hydrogen actually is 2 electrons and not just 1 electron. So it looks kind of like a little barbell, but it's a kind of a nice visual way to remind yourself that there really has to be 2 electrons involved in that bond. Now, this goes back to the electron dot thing that I mentioned. You will, if you surf through the web, you will sometimes see Lewis structures drawn like this, where instead of putting a line in between 2 elements, 2 atoms, they'll put the 2 dots like kind of vertically above each other. I dislike that kind of method. I am an advocate of actually using the line. So for the purposes of doing homework and things like that that are occurring over the next couple of weeks, try to stick to line equals bond, dots equal unbonded electrons, otherwise known as the lone pairs. All right, let me go back to better looking pictures than my horrid trying to use their whiteboard. All right. So let's have a look at a molecule that involves a carbon to hydrogen bond there. So we have a molecule here that has 1 carbon, 1 hydrogen, and 3 chlorines. So sort of continuing onward with the guidelines. 1 line per bond. Fulfill your duet and octet rules if possible. And keep in mind that for most of the molecules that we will be seeing, the first element listed in the molecule is usually the one in the middle. All right, so let's start with the valence electron thing. Carbon, 4th column, 4 valence electrons. Hydrogen, 1st column, 1 valence electron. Chlorine, that's the halogen column, so 7 valence electrons. And since I have 3 of the chlorines, I did my little 3 times 7. There's 21 electrons that actually came from the chlorine atoms. Total them up. I have to do something with 26 electrons. So I start with my tip idea of putting my carbon in the middle. I then surround my carbon with my other atoms, in part because we saw above, carbon likes to make 4 bonds. In fact, carbon is super unhappy if it does not have 4 bonds to something. So in this case, we're going to use 1 bond, 1 straight line, for each of the other atoms that's attached to. That way carbon's in the middle and it looks kind of like a plus sign in the way it's shaped. And actually, it doesn't matter which leg I stuck my hydrogen on. I put it on the top one, but from a building the molecule or even from a drawing the molecule point of view, it doesn't actually matter which leg you put the hydrogen on. So each of those lines, each of those 4 straight lines represents 2 electrons. So that means of my original 26 electrons, 8 of them have already been dealt with. Hydrogen is never, ever, ever allowed to make a double bond. It has a single bond and it's done. Also, due to the duet rule, you will never see dots around your hydrogen. Once it shares the one it brought to the party with its buddy, it's done. Chlorine, on the other hand, we're going to try to make these obey the octet rule. So I've got 18 more electrons. I would like to distribute them equally. So I will put 6 electrons around each chlorine. It's kind of traditional north, south, east, west. It doesn't have to be that way, but try to keep them so that they're paired, so that they look like 2 dots are kind of next door to each other. So if I'm looking at, for instance, my left-hand chlorine, it's got 2 dots above it, 2 dots kind of on the outside edge, 2 dots below, and 1 line. So each of those chlorines has an octet. It has 3 lone pairs and 1 bonded pair. And if you go back and you count them all up, I should end up with 26. This is why you kind of start with the how many idea. And then you begin your sketch, and you obey the rules as much as possible. And then you figure out if you have any leftovers. All right, let's pick on something with fewer electrons, but more bonds. So way back in the nomenclature chapter, we saw hydrocyanic acid, HCN. So if I'm going to draw a Lewis structure for this, back to the start with how many valence electrons I need to deal with. 1 for hydrogen, because it's in the first column. 4 for carbon. 5 for nitrogen. So I only have 10 electrons this time. This is also kind of a different shaped molecule because remember I said carbon really, really hates to not have 4 bonds. The only way you can make this molecule work is by sticking the carbon in the middle. You're not allowed to stick the hydrogen in the middle. It doesn't actually truthfully matter whether I write the hydrogen on the left-hand side or the right-hand side, but this is kind of a straight across molecule. I've got a single bond between my carbon and its hydrogen on the left. But because carbon really, really, really wants 4 bonds and nitrogen wants 3, I'm going to put a triple bond between the carbon and the nitrogen. But if I count up my lines, 1 on the left and 3 on the right, that's only 8 electrons. I have 2 more electrons I have to stick somewhere. Can't stick them with the hydrogen, that's not allowed. But I hadn't quite finished the whole concept of the octet for my nitrogen. So I'm going to take number 9 and number 10, and I'm going to kind of stick them on the outside edge. I could write them on the top, but I cut and pasted these from a whole bunch of different websites in terms of what the molecules look like. So this particular drawing of it draws them on the outside edge. Like I said, you could make them sit on the top, but they are with the nitrogen. So that gives me 10 electrons and I'm done. What about if we kind of roll back to the idea of the first atom goes in the middle? How about phosphorus trihydride? pH 3. So phosphorus is under nitrogen on the periodic table, which means it's going to have 5 valence electrons. Each of my little hydrogens has 1, so I have a total of 3 electrons there. And as far as the number of electrons go, this is a kind of minimal number of electrons molecule. I've only got 8. This one does definitely go back to the idea of put the first atom in the middle, because phosphorus wants more bonds. 1 line for each of the hydrogens, which means you still have 2 out of the 8 that have not yet been used. And if I do placement of that, and I kind of do this, actually it didn't want me, it won't let me do that. Okay, I was gonna try to highlight where the dots were there. But anyway, so the number 7 and number 8 sit on the top of the phosphorus atom. Now you will kind of notice that, and that this particular molecule looks kind of pointy. It's got the phosphorus on the top and it's got the 3 hydrogens kind of poking downward. I kind of grabbed images where I could grab them that were easy to copy when I was inserting them here into my notes. If you were doing this just on a sheet of paper, you would not necessarily have to do this so that all of the hydrogens are kind of all on one side. I could do something like this, okay? I could do phosphorus in the middle, and I could actually kind of spread them out more evenly. And yes, this is looks really awful here on my digital whiteboard, but I kind of get the idea. So I could actually spread them further apart if it's easier for you to draw it that way, but I still have to account for those 2 dots. Okay, so, and they still have to go with the phosphorus and not the hydrogens. So you could draw it this way if a question only asks you for the Lewis structure. It doesn't have to be drawn in a way that is more reflective of the actual geometry. And we will be getting to geometry in a bit here, as I try to flip back and forth between all my stuff here. All right, now we get to a rule breaker. So boron is a rule breaker. Boron wants less than 8, in part because it's small. Okay, think about where boron is on the periodic table. It's up near the top. It's at the top of a row. It only has 6 electrons total, 3 of which are valence electrons. So if I drew a Lewis structure of a BH3 molecule, I have 3 electrons that came with my boron. I have 1 electron that each of my hydrogens brought with it. But boron is okay with not having a full octet. It's happy the way it is. So you can stick the 3 legs on, kind of spread them apart, and I showed you where the angle is there at kind of about 120 degrees. And it's happy, and it's actually stable too. This is not a molecule that would fall apart easily. It spreads in the 3 equal directions. It's pretty stable. Note, there are no lone pairs anywhere. That will become more important later. So I have no leftovers. I used up all 6 of my electrons. Left-hand leg, top leg, right-hand leg. That's 6 electrons right there. I don't have any leftovers. I used up all I started with, so I'm done. I only had 6 electrons that I had to deal with. Now we begin to get deeper and deeper into things that earlier in the semester we kind of told you to take on faith. So let's talk about polyatomics. Polyatomics, one of the things we noticed early in the semester was they all have charges. And most of them have negative charges, but there's a couple that have positive. Ammonium, NH4, is one of the ones that has the positive charge, one of the very few that has a positive charge. So I'm going to account for kind of the why it has a positive charge. I have 1 nitrogen, 4 hydrogens, and then there's something that's missing. If you look at your nitrogen, my nitrogen has 5 electrons. I've got 4 hydrogens. So 4 electrons, because remember, we're only talking valence electrons here. Once this was assembled, one of the electrons went missing. It got stolen by somebody else. And that means I have 1 less. One of the things that you will notice for general chem, all bets are off if you take organic. But for general chem, we will not be dealing with odd numbers of electrons. Okay, odd numbers of electrons embrace something known as free radicals. That is a very deep subject for organic chemistry that has a lot of variants that kind of affect it. Just know that it happens. That's about all that we're going to do as far as addressing it. All the ones that we're going to look at have even numbers. So there's a couple of different ways that you can draw this. And I literally drew one of these with the whiteboard thing just so I could kind of give you a better idea on how it looks. Nitrogen goes in the middle because it's the first atom. Spread your 4 hydrogens around. Nitrogen kind of likes 3 bonds, but you can force it / coerce it into making 4. So 3 is the usual, 4 is what we're kind of making it happen here now. You will sometimes see it drawn 2 different ways. Now, sometimes it is useful, and especially in the final lab of the semester that we're going to be doing next week on Zoom, to put a very large pair of square brackets around the outside of the whole molecule and dump your charge kind of just on one corner. Typically, they write it on the upper right-hand corner, but it doesn't really matter. The other way you will see it, which is actually closer to reality. This goes back to that whole desired number of bonds point of view. So think about it this way. My nitrogen would be much happier if it only had the 3 bonds that it usually likes to. But you can force it to have a 4th bond because it doesn't violate the octet to make it have a 4th bond. It is actually more truthful to draw it the lower way, where you don't put the square brackets around it. You take the little positive sign and you write it next to the atom that is being forced to have an extra bond. So +1, because it really only wants 3, but you made it have 4, so Okay, all of this is a way of kind of just wrapping your head around the idea. It's a little bit more complicated than that in reality, but it still kind of boils down to the same thing. You can draw the plus next to the nitrogen because that's actually where the positive charge is. It's not really on the entire molecule. It's actually on the nitrogen and not on the hydrogens. And we're going to see variations on this as we kind of go further here. So what about the negative ones? Let's pick on sulfate. Sulfate's a nice, familiar polyatomic SO4-2. Remember back in the beginning of this, or back toward the beginning of the semester, chapter 2, chapter 3 stuff, we just kind of said, memorize it. No, it's SO4. It has a -2. It has a name. We're going to call it sulfate. Now we're looking a little bit more at how it's assembled. So back to valence electrons. This one has more than you think it should. My sulfur, which is actually under oxygen on the periodic table, has 6. But each of my oxygens has 6 also, and I've got 4 of them. So there's 24. And sulfate tends to steal electrons from other things, and it usually steals 2. So I have 32 total electrons. So first we introduce it with the square bracket method. Put your sulfur in the middle. And at this point, it does appear to obey the octet rule because sulfur has 4 lines. 4 lines, 8 electrons, everybody's happy. Each of my oxygens also has an octet. 3 pairs that are lone pairs, and the one straight line that connects it to the sulfur. And then you put the big square brackets on it, and you write the -2 on the outside. So this is true in a loose approximation, big picture point of view. In reality, not so much. So in reality, we have a moving conglomeration of double and single bonds. So look at the little circle there, okay, which is not really a circle, it's more like a rectangle. Start at the upper left-hand corner. So in that case, we have the north oxygen has a double bond. The east oxygen has a double bond. But the south and the west one each only have 1 bond. So now we get something that's actually a little closer to reality, where we have 2 unhappy oxygens because they don't have as many bonds as they would like. Therefore, we could write the negative signs next to them. But the problem is that this is not super stable. So the double bonds begin to rotate around the clock. You go from having north and east to north and south. And then eventually it's north and west. And then it kind of keeps on going. And we've got, as we go from the top row to the bottom right-hand corner there, we've got double bonds on the east and south, and then east and west, and then eventually on south and west. So in reality, this is like a spinning whirligig, spinning clock. Those 2 double bonds are in constant rotation. And there is a name for this. This is known as resonance. This rotating set of pictures is actually the true reality of the situation. Now, because they are in constant motion, you get stability. Because if you only look at one of those 6 little pictures in the rectangle, it would kind of imply to you that maybe this is not a super stable molecule, because 2 of the oxygens are definitely unhappy because they don't have enough electrons. And then it kind of rotates around. So it kind of gives you this idea that it might be likely to fall apart. But in truth, the fact that they do flip-flop around actually makes it incredibly stable. Let's back up a couple of chapters. When we were talking about precipitation reactions, one of the things we said is if you had, for instance, a sodium pair of molecules and then a sulfate, Na2SO4, so the 2 sodiums fall off, but the sulfate doesn't fall apart, not in just water. This is why polyatomics, many polyatomics, are made so much more stable because of the resonance issues. Resonance always implies that there's at least 2 options for what you're drawing. So let's go here to a different one. How about nitrite? NO2 with a single minus. So if I drew the 2 different variants, nitrogen goes in the middle because nitrogen wants more bonds to start with anyway. But I've got this flip-flop. It actually kind of looks like a windshield wiper. That double bond flops back and forth between the left-hand one and the right-hand one. So it kind of smears the negative charge around. So it's not strictly negative portion on the left and nice and neutral on the right-hand side. And it's not strictly negative charge on the right-hand one with kind of the left-hand portion of that molecule being nice and neutral. It kind of smears it around. That negative charge gets kind of distributed back and forth across the molecule, which is all about the stability. So we can't talk about resonance without addressing what I will refer to as like the prime example or the perfect example of resonance, which is a benzene molecule. And we saw the benzene mentioned a little bit briefly in passing back when we were talking about thermochem, and I said it would pop up again. So benzene is a hexagon. Take your 6 carbons, make a little hexagon, put each corner of the hexagon as a carbon. Then each carbon has a buddy who is a hydrogen. And so it kind of ends up looking a little bit like a Ferris wheel. And I have a whole bunch of different pictures here to give you kind of as many options as possible for how it sort of looks. You have alternating double bonds. You have, if you look at the very first left-hand picture there, you have a double bond at kind of 2 o'clock. And then you have another double bond down at about 5 o'clock. And then there's a third double bond over at around where the 9 o'clock is. But in order to be super stable, look at little arrows, look at little curvy arrows there. It goes flop, 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 flop. And your double bonds rotate. So if you sort of combine the first two pictures there, you look at the one labeled resonance hybrid, in reality, it's kind of smearing those double bonds into a circle, which is then why I kind of included some extra pictures here. I gave you the standard molecular formula, C6H6, and then I gave you, they call it the Kekulé structure, which gives you the two kind of normal looking resonance forms. And then I gave you the one there that shows you kind of how the bond angles look. If you were actually to build this or sort of draw this out, that kind of gives you an idea on kind of how you're supposed to distribute it. And then the lower row there with the orange blobs in it starts to come back to things from a couple chapters ago of sigma and pi bonds, but specifically the pi bonds, okay? Or the p bonds, rather. So if you look at the middle one there, remember p orbitals kind of look like two balloons tied nose to nose? What if you stuck them all in a ring and then you kind of smeared it around? And so the third little picture there that says delocalized pi system gives you a little hint about why the very last picture there, which is a hexagon with a circle in it, is a standard way of drawing a benzene, especially in organic chemistry. If you go on to take organic chemistry, or actually even if you take 112, we will do some organic chemistry, and you will see benzene rings often drawn as a hexagon with a circle in the middle. And what this is supposed to do is indicate to you that the resonance is a continual, ongoing event. It just like keeps on going around and around and around. Stable, incredibly stable. Somebody in lab asked me about making TNT, trinitrotoluene. The middle of a TNT molecule is a benzene ring. You put a carbon and 3 hydrogens on one corner. And then because of rules of organic chemistry, you get to rename it. It's now called toluene. And then you start putting NO2 groups on it. And the first one's easy. The second one's kind of rough. Getting that third one on, which is why it's called trinitro, makes the whole thing super unstable, which is why it goes bang. So all of this, in a lot of ways, is super, super based upon the idea of the resonance. You can make things super stable with resonance, but if you tip the balance too far, you can make things super unstable with too much resonance. So there are variations on a theme here. So we're going to mention formal charging. There's a little smidge about this, I believe, in your textbook. I'm just going to kind of wing through it just ever so briefly. This is not of terrible importance. I just want to make sure that I mentioned it because it does sort of play a part in the whys. When you're looking at things like the ammonium molecule, the ammonium ion, NH4+. Part of the reason why we draw the little plus sign next to the nitrogen is based upon this formal charge idea. The idea that if you took the number of valence electrons and you did this weird little calculation, which says subtract the number of bonds, and then also subtract the number of unshared electrons, and you have a leftover. So this is more wise. Just kind of know that this kind of gives you ideas that kind of go along with the, well, you can force something to have more bonds, but then it's unhappy. If you look at a chlor-8 ion, ClO3 minus, you would find out that some of the oxygens end up being negative, but the chlorine in the middle ends up being positive. So more reasoning. So just so that it has been sort of touched on ever so briefly, just sort of know that these sorts of things exist. So the last thing we're gonna then do tonight is a little bit of the molecular geometry. We have a great deal more to do on Thursday, but we're gonna kind of introduce a little bit of it tonight. Molecular geometry is 3 dimensions. So we can draw all these molecules on a sheet of paper with a pencil, and we kind of make this assumption that they're flat, which is not really true, because they are actual physical objects. If you have a scanning tunneling microscope, you can actually visualize them in 3 dimensions. Again, this is just kind of so you are aware that there are some other terms you might run across if you're, I don't know, reading other websites looking for additional examples or something like that. Sometimes you will see it called molecular geometry, which is actually probably the term I use most often. But you might also see it called molecular structure. You might see it called geometric structure. Why do we care? Okay, yeah, it's chemistry, but geometry changes properties. Geometry affects reactions and behavior. Some of this is dealt with more in the 112 class, and even more is dealt with in organic, especially on the reactivity end of things. All right. Geometry starts out with the Lewis structures. We're going to use something that we call Vsepr theory, V-S-E-P-R. It's one of those weird acronym things, 1 letter per word. Valence shell electron pair repulsion. All right, so there's two descriptions here. There's the textbook description, and then there's the more approachable description. So the textbook description starts with electrostatic repulsion, because you have repelling between electrons on the valence pair level. And as these are surrounding an atom, it causes them to be oriented as far apart as possible. All right. More realistic approach to this. All the electrons are negative, therefore they hate each other. And they want to be as far apart as 3-dimensional space will allow. Now, this takes it out of the realm of just Lewis structures alone. This takes it into the realm of we have to embrace that Z direction, X, Y, and Z, when we're talking about 3-dimensional space. We also need to cover all 13. Your textbook is not super great at covering some of the lesser known versions, but we have to cover all 13 versions, in part because you will also see some mentions of them in the upcoming lab. So there are 13 types. And we're going to start with the ones that have no lone pairs. So now I get to show off my Tinker Toys. We're going to come back to these again later. So this is one of the simplest ones. We will come back to all these names again as we kind of continue on through this, but to give you an idea on how this all sort of looks. So we've got this one that has one in the middle and one poking straight out on each side. These are called linear. We have a version that looks kind of like a fidget spinner, okay? It has a single atom in the middle and 3 equally distributed legs, but look at it this way, okay, it's flat. If I lay it on my hand, it is a flat molecule, okay? We're gonna dub this one trigonal planar eventually. Then there's this one, which has 4 legs, okay? And note, 3 of them kind of look like they're poking downward. I see this on the palm of my hand here. And one of them is kind of poking upward. But if I rotate it and I kind of flip it over, oh, it doesn't look any different, okay? If you have the same atom on each of the 4 legs, you actually have a equivalent molecule. This one's known as tetrahedral. There are other ones too, and this one actually I didn't get around to putting all my surrounding atoms on. We'll take a moment to do that. This one is one of the most unusual ones. This one has 5 legs. They're actually not all at the same angle. Okay. One is pointing downward. One is pointing upward. And if I kind of spin it, the 3 in the middle kind of rotate in their own little flat plane. Okay, this one's called trigonal bipyramidal. And I didn't build an octahedral one, but we'll come back to that. So let me talk about just 1 or 2 of these in terms of how they look when we're drawing them out. So here's some also generalities. I like to use, and many, but not all, textbooks like to use capital letter A as the one in the middle. B is used for the surrounding atoms. Now, your lab book does it different. Your lab book does it as A's and X's. And I have seen a couple of textbooks that use M's and X's. So if you're looking for additional examples, you might run across some other letters of the alphabet. I'm kind of fond of the A's and B's and E's idea. So what if you had that first one I showed you that had 1 in the middle and 1 poking straight out on either side? So its Vesepper formula is AB2. The word that represents its molecular geometry is linear, because the word linear means straight line. If you look at my wonderful pink and white picture here, you see that it has 180 degrees between the left leg and the right leg. Now, part of the reason that it spreads out into a completely straight line is I have no lone pairs on my center atom. There is nothing to exert additional force on those 2 legs. If I looked at mercuric chloride, okay, mercury 2 chloride, you would find out that my mercury has 2 valence electrons. Each of my chlorines had 7. So there's 16 in the whole molecule. Again, we're kind of shooting for that idea of trying to make everything happy. Okay, mercury usually only wants 2 bonds if it's in the +2 version. Because remember, mercury is a transition metal, so sometimes it's +1 and sometimes it's +2. But in this case, we're dealing with the +2 version. Draw each of the little pairs of dots around your chlorine. You have 1 line for each side of the mercury atom. That's 16 electrons. So I have 2 bonding pairs, no non-bonding pairs. And we are specifically talking about the mercury. My formula is AB2, which makes its geometry linear, and the bond angle is 180. This is when we're sort of heading in the direction of big picture. Once you draw the Lewis structure and begin to have an idea on what that Lewis structure represents, all of the other pieces to this kind of puzzle sort of interlock with each other. All of the things fit together to make it work a particular way. You'll have bonding pairs. You'll have non-bonding pairs. You'll have a Vesepper formula. You'll have a word or sometimes 2 words that represent the geometry, and you will have a bond angle or occasionally 2 bond angles. So last one I want to cover tonight is one of the other ones that has no lone pairs on the middle atom. This goes back to the trigonal planar thing. Boron. Boron is probably one of the favorites for doing trigonal planar. Actually, I can't quite fit all of this on the screen at the same time. So the formula is called AB3. A is in the middle, 3 legs. Trigonal planar, because if you draw it out and you kind of look at the way it's shaped, it's kind of a flat triangle. Back to the boron. Boron, remember, boron's happy with just 3 bonds and no leftovers. There's not very many ways to get trigonal planar molecules. Putting boron in the middle is the most common way. So back to my Tinker Toys for a minute. All right. So this one might represent my mercuric chloride, because here's my mercury in the middle, and I've got 1 on each side. And if I kind of look at it on end, it's perfectly straight. Okay. This is where I get my 180-degree angle there, because 180 degrees is an angle in geometry. It's a straight angle, but it's still an angle. Here's my little three-legged one. Okay. If I put my boron in the middle, as long as I have the 3 surrounding atoms, especially if they're all the same element. But when I look at it like this, okay, it's flat. This is why it's a trigonal planar, because trigonal pyramidal is something different, and that's the Thursday topic. So this gives you all the Lewis structure information. It gives you a little bit of your molecular geometry information. We have more molecular geometry to cover on Thursday, with hopefully finishing up polarity, sigma and pi bonds, double, triple bond stuff on Tuesday. So, okay, remember, we're nearing the end here, so kind of keep this all in mind of this is probably going to make your homework set due probably Wednesday night, okay, probably a week from tomorrow, so that I have 1 day for you guys to turn it in before I post the answer key. And then after I go over the answer key and do any other review stuff next Thursday, then you'll have that weekend for test number 4. And then you'll have a really, really fast turnaround, because then there's the final exam, which occurs in the next 2 days. And I know some people logged in later. The final exam is all going to be multiple choice. Okay, yes, there's math, okay, but it is all multiple choice. I'm probably going to put a slightly longer time limit. I'm probably going to put probably a 6-hour time limit for the final exam. Once I finish typing it, it's going to be 50 multiple choice questions. So they're all just 2 points apiece. And keep in mind that if you owe me things for lecture, or especially for lab, Monday night the 14th has to kind of be the last day for turning stuff in, because I need to do massive amounts of grading over the span of a couple of days. Questions?
Professor, are we allowed to go on campus for lab? Because
there are no more labs. There are no more physical labs.
physical, that's what I'm trying to find out. Okay.
There is one more lab, regardless of who you have for our department. All of us are doing the final lab of the semester, which is called Dry Lab 3, will be done via Zoom, because the college passed a ruling that after Thanksgiving break, there are no students allowed on campus because they're trying to make sure people don't infect each other.
Thank you, ma'am.
Especially for people who travel, not all that kind of thing.
Thank you.
So like my people have lab on Monday the 7th. You need, if you have somebody else for lab, either Wheaton or McHugh or Seniac, you need to check with them to find out if they are doing their dry lab this week or next week. I postponed mine till Monday the 7th because I wanted to make sure we got through as much of the molecular geometry as possible prior to doing the lab. People who have Wheaton and McHugh and Seniac might have lab this week on Zoom. You need to check with your lab professor. Other questions? Otherwise, more Tinker Toys on Thursday. Things I have bought to do my job. I will see you then.